In the second part of 7.3, we're going to talk about fission and fusion, which are two specific types of nuclear reactions that can be used to harness a significant amount of energy. First, let's talk about fission. Nuclear fission is when a large atom gets split up into two smaller pieces of roughly similar size. And so we're starting with a very large atom, a very large nucleus, and breaking it down into smaller nuclei. And in that fission, think about a fissure. A fissure is a crack in the earth. It's a large crack. It's where it opens up or tears apart. Fission is when the nucleus tears apart or breaks apart. And in that breaking apart, there's energy released. And that energy comes from that idea that we talked about before of binding energy. And so the binding energy that's associated with the two smaller nuclei is less than the energy associated with the larger nucleus. And so the extra energy gets released into the environment. And the process of nuclear fission is not one of those natural transmutations or the natural decays that we talked about, so it has to be induced. We have to use something to get it going. And the most common way that this is started is by the introduction of a high energy neutron hitting the nucleus of that large atom. Okay, so here we have a sample, and actually I should put our numbers here for our neutrons, 0 and 1, atomic mass of 1. And let's figure out what this unknown nucleus is here, this X. On the left-hand side, we have 92 protons. We have a total atomic mass of 236. Over here, this 2n, because the 2 is a coefficient, it tells us that the neutrons are separate. So we have two separate neutrons. So we have a total accounted for proton number of 38. So to find out how many our unknown element has, we're going to do a little simple subtraction. And so that's going to be 54. And so our unknown element is 54, X, and atomic mass over here we have 93, 94, 95 that's accounted for, 236 over here, so 236 minus 95 is going to give us 141. 141. If we look at our periodic tables, atomic number 54 happens to be xenon. So there's our unknown. Now, when we look at this reaction, if we were to go through similar to how we did with our nuclear reaction, the practice problem that we worked through, we would find that the energy or the mass that's associated with our single neutron and uranium-235 on the left is larger than the mass associated with the four particles produced on the right, the xenon, strontium, and the two neutrons. And so the total mass on the left is going to be larger than the total mass on the right. Why is that difference there? Because some of that mass has been converted and released as energy. And so this is how we get energy from fission reactions and from fission reactors. The other process is nuclear fusion. When you think about the term fuse, if something is fused together, it's joined. Nuclear fusion is when we take smaller particles, generally hydrogen and helium nuclei, but they can be larger, and we fuse them together to form larger nuclei. And again, though, in that process, the resulting nuclei have less energy than the constituent particles, and so there's extra energy released into the atmosphere. If we trace it back far enough, that's where all of our energy on Earth pretty much comes from, except for geothermal, because the sun's primary source of energy is nuclear fusion. And if we look at just how much energy is produced in a fusion reaction, we can take the process that produces a deuterium nucleus from a proton and a neutron. So here we're taking a proton and a neutron, joining them together to form a deuterium nucleus, which is that 1H2. It's the hydrogen nucleus that has a proton and a neutron. And so, looking at our reaction here, our hydrogen nucleus and our neutron, here's our product, our deuterium, plus this is just energy. And so, if we look up our masses, a hydrogen nucleus, which is just a proton, has a mass of 1.007825 atomic mass units. The neutron, and you might remember that the neutron is slightly larger, and this can be seen here. The neutron has a mass of 1.008665 atomic mass units, and so here is the total mass of the products. Now, if we then look up the mass of our deuterium atom, we find that it's down here, it's 2.014102, and that gives us a mass difference or a mass defect here of 0.002388 atomic mass units. Converting that into mega electron volts, we find that there are approximately 2.22 mega electron volts of energy released for every reaction that fuses a proton and a neutron together. Now let's use the graph of binding energy per nucleon to compare fission and fusion a little bit. Fission occurs, as we said, with larger nuclei, and generally ones where the atomic mass is greater than 200, so more than 200 nucleons. And when fission occurs, remember that the daughter nuclei are roughly half the size. Okay, so about 100. So we're talking about this range in here for our parent nuclei and our daughter nuclei. And you can see here how gradual the slope of this line is. And so the daughter nuclei, though, have a higher binding energy than the lower ones. So if you look at the daughter nuclei have higher energies per nucleon, which means they're more stable. And so since these have a higher binding energy, that means that they've released energy. That energy goes into the environment. Over here on the left-hand side, this is where our fusion occurs, over here with our smaller elements. And so we're going from things like H1 and H2 up to helium and lithium. Now, if you think about the slope of this line here and the slope of this line here, and you start looking at how steeply this goes up, it should give you some explanation as to why fusion reactions give off so much more energy. And it's because the energy per nucleon changes so much more drastically. And so when we go from smaller nuclei with very low binding energies per nucleon up to even just a couple more up to the helium and the lithiums, the binding energy per nucleon is much, much greater. It changes much, much more quickly. And so again, though, they're much more stable. And so the energy released per nucleon for fusion reactions is much larger than for fission. Energy per nucleon released is much greater for fusion than for fission. All right, now just a couple other things about these two processes, and more in kind of the practical vein. Fusion releases more energy per nucleon. So why don't we have more fusion reactors? And the reason is because of the enormous amount of energy it takes to get the process started. And this can be seen just on the sun or in stars. Stars emit light and heat through fusion. That's the process that produces all of that energy. And it's an enormous amount of energy. and it took an enormous amount of energy to get it started. Now, once it got started, it's going to keep going until its fuel gets used up. But right now, on Earth, we haven't established fusion reactions that give off more energy than it takes to get them going. We can't sustain them and make it cost effective. We can't get a benefit from the energy. We don't get more energy out than we put in at this point. So you hear things like cold fusion. And when you hear that term, it's not really cold. It's not what we think of as cold. It's just at a much cooler temperature using much less energy than we have it at this point. And it's getting better and better, and the technology is getting better and better, but we're still not to a point where it's a viable means of energy. So it takes a lot to get started. And then fission reactions are what are going on in nuclear reactors around the world. Whenever we talk about nuclear reactors, that reaction that's going on is a fission reaction, and they're generally starting with some isotope of uranium, and it's undergoing that fission reaction where we add the neutron, and it breaks it up, and it releases energy. And if you notice, in the reaction, you got 2 neutrons out of it. And so fission reactions are what we call chain reactions. And so you have 1 neutron that's going to hit a uranium nucleus and create the fission process. And from there, you're going to have 2 neutrons released. And each of those neutrons maybe hits a uranium. And from each of those, you have 2. And so you can see how this just keeps getting larger and larger and larger. And so in nuclear reactors, they actually have to have control rods, which are materials that absorb a certain amount of those neutrons so it doesn't just become uncontrolled. Atomic weapons that use fission reaction are uncontrolled fission reactions. It starts out as one reaction and it just multiplies exponentially, and that's why all that energy gets released so quickly. But in nuclear reactors, it has to be a controlled fission reaction, so they use control rods, which are materials that absorb neutrons, and so when you get to a certain point, only a certain number of those neutrons are actually going on and continuing on and creating another fission reaction. And so you maintain a steady pace of fission reactions to generate just enough energy to boil the water, turn the turbines, and generate the amount of electricity that you need from that particular power plant. And if it gets out of control, that's when you start to have things like nuclear meltdown, the power plants overheat, and that's when all the trouble begins.